accelerating data science. Speaker is McKercher from NVIDIA for this one. So.
Hey, hi. So today I'm going to put on my open source hat and share with you some of the things that maybe you haven't seen with regard to accelerating machine learning APIs, and including Pandas APIs as well as scikit-learn in a project we call Rapids. This is all put out in the public domain, open source. It's moving very rapidly, and so I welcome you to experiment with it and at least learn what we're doing there. I realize this is an HPC conference. We think that it's exciting to use the machine learning APIs to help accelerate the science. It's really physics-guided or technology-guided data science. Think of it that way. So I have three main areas. I have 15 minutes, 5 minutes in each area, I hope. First, I'll talk about why we're doing Rapids, then talk about how it works, how Rapids works. And then finally, since this is HPC, talk a bit about distributed computing. Teaser, I just ran a 3.2 petabyte array, GPU array, across a cluster of nodes in less than an hour doing a prefix sum. I'll share more about that in a minute. Okay, why are we doing Rapids? Well, it's obviously there's a data explosion, and it's not just, this is very familiar with the seismic industry, but it's about trying to accelerate that workflow, look for opportunities where there's time that's being spent. We realize there is time being spent. It's very painful in data science to do the data preparation. It takes a lot of time. We know this because there's checkpointing going on. Anytime there's checkpointing, that hurts, because it took a long time to get to that point. You want to checkpoint it, so if something goes wrong, you can get back to that. So what we're looking for is opportunities to accelerate parts of the workflow. So to do that, we look at, say, the Kaggle contest. Kaggle attracts some of the best data science minds that there are. They pay them big money if they can win a contest. It's driven by a science-type problem. It's like we want to try to figure out how to accelerate a workflow or uncover some kind of science. So we search for different kinds of surveys to see what's being used in the community. And you can see from the chart that most of the time is indeed spent on just gathering data, doing data pre-processing, data preparation. That's an area for opportunity for acceleration. The other one that jumps out is around model building, just iterating over and over and over again, building models. But there's acceleration opportunities all throughout this workflow. We're just looking for areas where we can potentially help. So the question is, what's your typical data size? This was the survey data from Kaggle was about, I think, late 2017 when we got this data. So we're seeing more and more of the shift more toward the higher end nowadays. But typical for these types of projects, they're working in the 1 gigabyte, 10 gigabyte type range. Obviously, in this industry, you're well on the other end, the far end of the spectrum. But I have some news to share about distributed computing, talking about petabyte type operations with some of the stuff we're working with. All right, so the question is, which APIs are most used? What do they use for what methods? So one that really jumps out, the tried and true logistic regression. Those are opportunities for acceleration, and we have some of that today within Rapids. But there's also a big area of interest and really good opportunity around decision trees and random forests and so forth. The reason being is it's already been parallelized to run across a distributed cluster. So you can run with multi-node, multi-GPU distributed with these decision trees. But more importantly, that's also how you can get very accurate predictions or classifications using these types of decision trees. To help explain a little bit more about decision trees, I like this example where think of each swing of the golf swing is a decision tree. And every iteration of that, you want to try to get closer and closer to your target. And the way in which you can get there is learn from your mistakes in the first one and correct and always minimize to get to an accurate result. And the power of these algorithms is in chaining these different trees together. Turns out that these trees can be run in parallel, and not only in parallel, but distributed parallel. Another question we're asking for the data science team is, since you're spending so much time manipulating data, what methods and what mechanisms and APIs are you using for data manipulation? Pandas just clearly jumps out. Anything to deal with a data frame. Take data, put it into a data frame and combine it, maybe group different elements together, join things together, merge, sort, so on and so forth. So these are the areas we're attacking first, those areas where they're the highest importance. And we've accelerated parts of the Pandas API. Not all of these are accelerated today, but it is open source and it is moving rapidly. So again, the reason we're doing Rapids is help the data science community, really. That's the main point here. But it's also important to stay where they are. Stay in the world of familiar. They use Python. They use Pandas. They use scikit-learn. Try to match the APIs so that they're very close to that, and it's not too hard to be able to accomplish the goal. Get better acceleration. So that's my first section. This section is kind of just a little dive into how Rapids works. Again, these are the workflow is across the top, where a lot of the work is spent in data preparation, then model training, and visualization. What we are delivering in the open source today is cuDF for CUDA accelerated data frame manipulation. It's very much like Pandas API, and you get acceleration. We have significant opportunity to import data into the GPU and then be able to do data manipulation. cuML is for machine learning. It's very much like scikit-learn. Many of the very popular scikit-learn algorithms have been accelerated on GPU. Many that we're continuing to evolve that and looking for this community to give us some feedback and input on where we can spend our efforts as well in that area. We have a library for doing graph analytics. It's not graphics. It's actually helping with these decision trees, and many of these problems can be broken down into a graph, and you need a library to be able to accelerate that quickly. We do feed into our deep learning roots as well. They're very complementary. People are using machine learning to help do better classification, prediction, to feed into deep learning and iterate back and forth throughout that whole process. And at NVIDIA, we wouldn't be NVIDIA if we weren't doing something visual. And so we have some really interesting libraries that works there. It's important to be able to gain insight into this massive amount of data, and visual information can be very powerful. Sorry. So if you wanted to get a good feel for what this is like on the end-to-end, we have a GitHub repo. One of the solution architects at NVIDIA wrote this, but it's an interesting IPython notebook where we're taking many of the data science type data sets. In this case, there's a Swiss roll. It's hard to see, but there's half moons in there, and then there's blobs. These are all 3D, and in the notebook, you can rotate around and look at this. What we're mixing in here is the training and evaluation test set. So the yellow dots are for test. The other one's for training. Okay? So what the notebook will do is walk through the different methods for doing prediction or classification to try to classify these different types of objects. And on the left, you see XGBOOST result, and on the right is a combination of taking the output from XGBOOST, these decision trees, and add it through a density-based scanning machine learning algorithm, and then ultimately you get a much, much better result as a result of combining these different types of models. So wouldn't it be fun if You do this manipulation of the data. You're reading from pandas. The data gets onto the GPU. And then once it's there, I can operate on it. I can run an XGBOOST model against it. I can feed that into a density-based scan model. It's on the GPU. I could run some GPU-accelerated algorithms that I already have that are HPC type oriented or simulation type oriented. The key here is that we have a common data format called Arrow. And there's a columnar part of the specification for Arrow. And you write that data into that format. Others can benefit by using that same format, reading from the same format once the data is on the GPU. And it's not just one GPU, it can be a cluster of GPUs that you share that data from. Again, the API, we want to keep the familiarity. So scikit-learn, pandas, Python. This is the piece of code on the top is what the data scientists use today for scikit-learn. On the bottom is what you would do for QML. It's very much the same or very similar API. Again, that's really, really important to stay in something that you're familiar with to be able to take advantage of this technology. All right, this is just an example of one of the projects that one of the engineers on the Rapids team did. He submitted an entry for trying to help classify different elements in the universe. And I just put this chart up here to show how Rapids can integrate with TensorFlow and so on and so forth. So you're using elements of both machine learning and deep learning interchangeably. All right, so this is the last section, and it's on distributed computing. I was able to run a 3.2 petabyte GPU array spread across a cluster of 20 nodes. I use 19 of them for doing the processing. Each of the 19 nodes had 4 GPUs with 16 gig each. And basically the operation that's being done here is a prefix sum or a reduction sum. And it 3.2 petabytes in less than 54 minutes. Less than an hour. I have the whole configuration here. I have the code. If you're interested, come see me. We can talk about how you can duplicate this. I also wanted to illustrate how you can scale out. So it's not just big clusters, but also smaller clusters. Data scientists maybe have workstations beside them. Laptops are becoming even more popular. But if you're working on your local system, can get you so far. Can use the same technology to go scale out. And I run some tests on another cluster configuration, a smaller size, 2 terabytes, but still operating with 2 terabytes across 8 nodes with, 4 nodes with 8 Tesla T4s in 25 seconds. So there's some real value associated with this process. So how are we able to achieve this? What are we doing here? Well, this is a stack. This is the chart. I already talked about cuDF, cuML, and cuGraph. Apache Arrow, again, is that common data format. But this thing on the right here is called DASK. DASK is a Python library. And it's really used to help split data across many GPUs. You can do the many GPUs in one server, or you can do many GPUs distributed across the cluster. It's written in Python. DASK is written in Python. It has a modular design, but it is also adaptable to the HPC world. So if you're running and you have a clustered system and you have some kind of scheduler in the front, you can easily add that to that HPC cluster through Yarn or through Kubernetes, Slurm, PBS, whatever the case may be. Under the covers, what DASK does is it takes a problem and it breaks it into a task graph. And it allows you to work with the data in the collections, and I'll get into this in a little more detail in a second. But it also works with schedulers. So you start a DASK scheduler, you have workers that are spread across network of nodes or on a single node, and you basically can do communication between the scheduler and the workers in a resilient fashion. And it's totally distributed. If one of those workers happens to die or go away, no problem, it continues on seamlessly. But again, the whole notion is to be able to break this problem into a task graph. So each node represents a different function, and then each connection between those is some kind of communication point. So for the problem doing the array sum or prefix sum reduction, I used DASK arrays. And these are multi-dimensional, n-dimensional array structure support. That's part of NumPy. But it's put it in this framework where you can go distributed. You can break this big problem into a bunch of small problems and spray it out across a cluster network. And DASK handles that for you. Okay? This is an actual snapshot of one of the monitors associated with DASK that you can see under the covers as it's doing its computation, what's going on. And so this is, again, 500K by 500K data of doubles. So that's 2 terabytes of data. Each node out on the end is representative of various types of operations, and then there's connections between them. You'll notice that some are blue. This is actually moving up as it's progressing. Blue means that it's been released. Red means that it's in memory. And green means it's processing. And the gray means that it's waiting. So in essence, this is many HPC applications benefit from a reduction sum. And this is exactly the kind of work that's being done here. And I unfortunately don't have the PowerPoint, but this would be animated to show you what it looks like on the other part of the DASK monitor. Each one of those horizontal bars across the top is a different Python process, a different process that's managing all these tasks and doing these kinds of communication. So as you go from one level to the next, you get this big reduction. So over time, there's synchronization points, and it progresses very smoothly as you go through. You're also striding through data, and there's a get item, there's a sum, a partial sum. As you're doing these partial sums, you're accumulating along, and at the very end, you do the aggregation and sum up the whole problem. 2 pages of code. I'm not going to go through all of them here, but 2 pages of code to accomplish this. Anybody's interested, come see me. Maybe what we do is get a WebEx together. We could talk about some of this kind of stuff. All right, so it is open source. Open source means there's continuous improvement, continuous development. They do a nightly build of version 0.6 right now. You want to get close to our engineers to help them solve your problem? Download this stuff and go play with it. Submit a GitHub issue or a GitHub pull request. If you got some ideas and ways to contribute, jump in here. Let's get some SegWhy readers going, shall we? We're just reading CSV files, so let's get busy. But there's a serious cadence here, too. I mean, this is like moving along, and it's not just us at NVIDIA. It's an ecosystem, because you're landing on Arrow, the Arrow format. That's an interchange opportunity to share data. Code's out there. If you want to see it, go look at the code. Pretty cool. So you want to know more, there's rapids.ai is your point. So if you click Get Started on rapids.ai, there's examples how you can actually take advantage of this technology right away. I was inspired by that blog article to do this whole distributed prefix sum example that I shared. There's a notebook in that blog article. Really cool, really cool. Terabytes worth of data in seconds. And then it's also, if you want to hook some of this distributed computing into your HPC world, there's some nice pages up there. Finally, the last one is the APIs for doing QDF and QML. A lot of the documentation has examples where you can cut and paste right out of that and learn as you go. That's it. Any questions?